This is your presenter, Asloob Mudassar, and I am presenting slide number 6 of the course on atomic and molecular physics. The following topics will be covered today: extension of Bohr's model by Sommerfeld, lifting of orbital degeneracy by relativistic mass change, limits of Bohr-Sommerfeld theory. Extension of Bohr's model by Sommerfeld. When viewed through high-resolution spectrometer, the spectral lines in the Balmer series are in fact not single lines. Each line consists of several components. You see that in the previous lectures we have discussed the Balmer series, and we have shown that there is only a one single wavelength emitted in the Balmer series, and that is shown as a dotted line over here. That is, the dotted curve indicates a single emission of a wavelength through a spectrometer which is low resolution. But if the same dotted curve, that is a single Balmer series line, is viewed through a very high resolution spectrometer, then you can see the other details in that one. For example, here in this particular case, you can see that there are two main peaks, and there is also a small peak over here, and the separation and the two main peaks are separated by a distance of by a energy of 0.33 centimeter inverse. So it means that a high resolution spectrometer would help us to resolve or to see the actual structure that may appear in a line from the Balmer series as shown in this figure. And this figure actually belongs to H alpha line. And you know that H alpha line is the first line of the Balmer series when the transition takes place from the level n is equal to 3 to n is equal to 2. And the line that is emitted is referred to as the H alpha line. So this is H alpha line viewed through high resolution spectrometer. If we talk about that a single Balmer series line is emitted, then the dotted line will represent, or the dotted curve will present a single H alpha line. But that if this line is viewed with a very high resolution spectrometer, then you can see more details and more structure in this in the single Balmer line and you here in this particular case you will see that there are two peaks and which are separated in energy by 0.33 centimeter inverse. Here new bar of H alpha line has a value of that is the central wavelength corresponding to the peak value of this dotted line has a wavelength, has an energy that corresponds to 15,233 centimeter inverse. And this line consists of multiplets with a wave number splitting of delta nu bar is equal to 0.33 centimeter inverse between the strongest components. So you see that here between the strongest two components, I have shown that the separation between these stronger components in terms of the wave numbers is 0.33 centimeter inverse. And the central wavelength of corresponding to this Balmer series, that is corresponding to the peak value of this dotted line, which is emitted as an H alpha line, has a wavelength of corresponding to the energy of 15,233 centimeter inverse. The spectral resolution required to split to see the details of this H alpha line, which is shown in the dotted line over here. And if you want to see the detail of this one, you need a very high resolution spectrometer. And that spectrometer must satisfy this condition. That is, the spectral resolution required should be equal to nu bar over delta nu bar. So nu bar is given over here, which is 15,233 centimeter inverse, and delta nu bar is given as 0.33 centimeter inverse. So if you make a decision by substituting these values over here in this formula, you can roughly get that the spectral resolution required should be equal to 100,000 times So such a spectrometer with this much resolution is required if you want to see the further details or the further structures in the emission of the H alpha line of the Balmer series as shown in this figure. It is the Doppler broadening that smears out the structure detail and thus limits the resolution. So you see that the Doppler broadening, which we have already discussed in the course on atomic physics in much greater detail. If you want to see what is the Doppler effect and how it influences the broadening mechanism, then you must consult one of the slides covered in the course on laser physics. So it is the Doppler broadening that smears out the structure detail and thus limits the resolution. In the spectrum of the helium singly ionized ion, which is similar to hydrogen-like atom, these multiplet lines are more strongly separated, and the splitting is easier to observe because the splitting increases with the power of z to the power 4, where z is the atomic number. So you see that here the splitting is shown, but if you are talking about such a similar structure for the helium singly ionized ion, then of course this separation will be well broadened because the helium has a greater atomic number. And so the splitting goes as z to the power 4. Sommerfeld generalized Kepler's laws for atoms and said not only circular orbits but elliptical orbits are also possible having the same energies. So you see that this is an addition of the Sommerfeld model using the Kepler laws. Then he introduced elliptical orbits along with the circular orbits suggested by the Bohr. So elliptical introduction of the elliptical orbits having the same energy as that of the circular orbits is a new addition due to the Sommerfeld. To distinguish the elliptical orbits from the circular ones, he introduced a new second quantum number. The total energy of a term is determined by the principal quantum number n according to Bohr's theory. So this En, which is the binding energy of the electron in the nth state, is equal to minus, in the numerator we have Rydberg constant of the hydrogen atom multiplied by Planck's constant H multiplied by C multiplied by Z square, which is the atomic number of the atom divided by n square. So this is the formula that was given by the Bohr's atomic model. And you see that here the energy of an orbit depends of a circular orbit depends only on the principal quantum number n. But you see that in the above, as I stated, that the Sommerfeld also introduced elliptical orbits, and also with that one he introduced a second new quantum number. N determines the major. You see that according to the Sommerfeld, and since there are two quantum numbers now, N determines the major semi-axis of the elliptical orbit, whereas the minor semi-axis is determined by the second quantum number in such a fashion that that L mod, that is the magnitude of the orbital quantum number, is equal to k times h bar, where k satisfies this condition that k is less than equal to n. So you see that here k is a second quantum number. According to Bohr model, we have seen that the magnitude of the orbital angular momentum was equal to n times h bar. And there you see that you had n as the principal quantum number that discretizes the value of the orbital angular momentum of the atom. But here instead of n, you have k quantum number. So the mod of the orbital angular momentum will be equal to, according to the Sommerfeld theory, will be equal to k times h bar, where h bar is the reduced Planck's constant, k is the principal quantum, k is the quantum number, second quantum number introduced by the Sommerfeld, and that satisfies the condition that k should be less than equal to n. You know that before that we have seen similar relationship over here, but that relationship was in the form of a principal quantum number n replacing the quantum number k. Now you see that here, according to the Sommerfeld, we have the quantum number k, which has replaced the principal quantum number n suggested by the Bohr, because the Bohr suggested circular orbits, and according to the Sommerfeld, the orbits could be elliptical. So you see that the elliptical orbits satisfy this condition, that the orbital angular momentum of the atom of the system will be equal to k times h bar, where k satisfies this condition, that k is less than equal to n. The mod of L is actually the absolute value of the orbital angular momentum, which we have also stated earlier when we were talking about the Bohr atomic model. Later, the Sommerfeld second quantum number k became the orbital quantum number L, where L is equal to k minus 1. So you see that here Bohr introduced the quantum number k, but later we found that this k quantum number is actually the orbital quantum number. And you know that this orbital quantum number L is related with the quantum number k of the Sommerfeld through this relationship, that the orbital quantum number L is equal to k minus 1. So the orbital angular momentum is represented by the mod of L, that is the absolute value of the orbital angular momentum, and the orbital quantum number is simply represented by the small l, and L is related with the Sommerfeld quantum number through this relationship, that is the orbital quantum number L is equal to k minus 1. Now you see that in the atomic physics, we don't talk about any further about the quantum number k suggested by the Sommerfeld. Instead, we talk about the orbital quantum number L, because the relationship is only differs by a value of unity. So L is equal to k minus 1. Instead of talking about the value of k, we shall be talking about the orbital quantum number L through the rest of the atomic physics. The length of the minor semi-axis, also known as the eccentricity of the ellipse, has no effect on the total energy, but controls the shape of the elliptical orbit. So you see that this is again a suggestion of the Sommerfeld model, that the value of L or the k value or the k orbital or the k quantum number, or in principle the more accurately the orbital quantum number L does not that is the energy does not depend upon the value of L, but of course L would help to determine the shape of the elliptical orbits. We shall see later that the magnitude of L is equal to square root of L into L plus 1 times h bar outside the square root, where on the left hand side the mod of L is actually the magnitude of the orbital angular momentum of the atom, whereas small l on the right hand side under the sign of the square root is actually the orbital quantum number. So you must have a difference of these quantities. That is, the L mod on the left hand side represents the absolute value of the orbital angular momentum, whereas L on the right hand side is actually simply the orbital quantum number. And the two quantities are related through this relationship, where L now starts from the value of 0, 1, 2, 3, and so on up to the value of n minus 1. And if you talk about this relationship in terms of the quantum number k suggested by the Sommerfeld, then of course k value will start from 1, not from 0. So k starts its value from 1, 2, 3, and so on up to the value of n. Whereas L, if you substitute these values over here, whereas the value of L will start, for example, following this relationship, that L is equal to k minus 1. So k starts from 1, 2, 3, and so on up to the value of n. And similarly, if you substitute the value of k over there, then of course the value of the orbital, allowed values of the orbital quantum number becomes equal to L is equal to 0, 1, 2, 3, and so on up to n minus 1. So now equation 3 is the equation that we shall adopt for the rest of the atomic physics. That is the magnitude of the orbital quantum number, that is the magnitude of the absolute value or the absolute value of the orbital quantum number L of the atom is related to the square root of the L into L plus 1 times H bar, where H bar is outside the square root, and the values of L varies from 0, 1, 2, 3 and so on up to n minus 1. Here we are using small values of L. It means that we are talking about an atom which has only single electron. For example, hydrogen atom or the hydrogen-like atoms which have only one valence electron outside closed inner shells of the electrons. So in such cases, when only one electron is involved in the formation of the orbital angular momentum of the atom, then of course we shall use these quantities in small alphabets. That is, L will be small, L mod, where L is a small alphabet, will be representing the absolute value of the orbital angular momentum of the atom, and the L on the right hand side will represent the quantum number when only single electron is involved. The mod of L is the magnitude of the orbital angular momentum, and L within the square root is the orbital quantum number. For each value of n, there are n values of L. That is, there are n values of orbital quantum number, going from 0, then 1, 2, 3, and so on up to n minus 1. Thus, each energy term is n-fold degenerate. That is, if the principal quantum number n, then there are n-fold degenerate values. For example, n0, n1, n2, and so on up to n, n minus 1. These would be the values having same energies, though with the different orbital shapes. So when some levels have the same energies, we call such levels as degenerate levels. And these n levels, starting from 0 value of orbital quantum number L, and the last value of quantum number L is n minus 1, and the first index represents the principal quantum number in each parenthesis, whereas the second quantum number represents the value of the orbital quantum number going from 0 to last value of n minus 1. So you see that these will be n-fold values, and these n-fold values have the same energies, though corresponding to each parenthesis, the shape of the electron orbital will be different. And these n-fold degenerate values, because these have the same values of energies, that's why these are called the degenerate levels. And you see that in one of the previous Grotrian diagram or the term diagram related with the hydrogen atom or the hydrogen-like atom, we have seen that when n is equal to 0, then there is only one level. So when L is equal to 1, when the principal quantum number is equal to 1, then there are two levels. When the principal quantum number n is equal to 2, there will be two levels, and when the principal quantum number n is equal to 3, there will be three levels. So all those levels were degenerate levels. So if you wanted to see the, I would suggest that at this stage you go through the first and the second slide of this course and look at the Grotrian or the term diagrams and see how many levels are there. That is, when the value of n is equal to 1, how many levels are there? There will be two levels. So when the value of n is equal to 2, there will be three levels and so on. You can check these one in the previous diagrams. So you see that when the principal quantum number is 1, how many levels will be there? One level. You see that the principal quantum number starts from n is equal to 1, 2, 3, and so on. So when principal quantum number n is 1, there is one level. When the principal quantum number n is equal to 2, there are two levels. When the principal quantum number n is equal to 3, there are three levels. in the Grotrian diagram or in the term diagram. So corresponding to the value of the principal quantum number, the number of levels in the term diagram would be equal to the number of a principal quantum number. So if the principal quantum number is 5, then of course there will be 5 levels having more or less the same amount of energy. And this is what you can confirm from the previous slides, from the Grotrian diagrams or the term diagrams given in slide number 1 or in slide number 2. The spatial form of the electron orbits. The spatial form of the electron orbitals will be discussed later on in the course. So you see that here I have suggested that N0, N1, N2 and so on, these would have different orbital shapes, and these shapes will be discussed in the rest of the course. Here L, the magnitude of L and the term symbols are presented in the next slide. For example, over here you can see that the orbital quantum number L has possible values 0, 1, 2, 3, 4, 5. We have listed only 5 values over there starting from 0. So there are a total of 6 values of the quantum number L, of the orbital quantum number L, that we have given in the first row. Now the orbital angular momentum. The orbital angular momentum is given by the relationship from equation number 5.3, that is from here. You substitute the value of L, quantum number, on the right hand side, and you can compute the magnitude of the orbital angular momentum, which is given in the second row of this table. So orbital angular momentum, the magnitude of the orbital angular momentum represented by the mod of L has a value equal to 0 h bar, square of 2 times h bar, square root of 6 times h bar, square root of 12 times h bar, square root of 20 times h bar, square root of 30 times h bar. So these are the values of the orbital magnitude of the orbital angular momentum. Now the symbols associated with these values, that is the symbol associated with the values of the orbital quantum number. For example, when L is equal to 0, the term symbol will be represented by S. When L is equal to 1, the term symbol will be represented by P. When L is equal to 2, the term symbol will be represented by D. When L is equal to 3, the term symbol will be represented by F. So for L is equal to 4, the term symbol is G. For L is equal to 5, the term symbol is H. So you see that these we have associated term symbols which are associated with the value of the orbital quantum numbers, and these will be frequently used in the atomic physics course. You see that in the previous equation, that is in this equation, in equation number 5.3, we have used small alphabets to represent the orbital quantum number L and the magnitude of the orbital angular momentum L mod. So you see that these are in small alphabets because we are talking about only a single electron that is contributing to, or that is contributing to the angular momentum of the atom of the electron. So when the atom of the electron has an angular momentum arising due to a single valence electron, then of course we shall use small alphabets as shown in equation number 5.3. But if 2 or more electrons involved, then of course the values will be represented by the capital alphabets. So here, for example, in equation number 5.4, capital L mod on the left hand side is related to the capital L on the right hand side, that is capital L into L plus 1 times h bar. Here capital L on the right hand side represents the total orbital angular momentum of the atom, whereas the mod on the left hand side, mod of L on the left hand side, represents the magnitude of the orbital angular momentum, or the total or the magnitude of the total orbital angular momentum of the electron when it is arising by at least 2 electrons or more electrons. Let us consider the case of an atom having 2 electrons in its outermost orbit. And here we are assuming that the inner orbits are closed orbits. The electronic configuration of the last two electron is 2p3d. This is what we are assuming, that an atom has two electrons as the valence electrons lying outside the closed inner shells. And these two electrons, for example, are 2p and 3d electrons. It could be an excited state of the atom, for example. For the 2p electron, we have L1 is equal to 1, because since it is a single electron, we are using L1 as a single L1 as a small alphabet, in small alphabet. So the orbital angular momentum for this 2p electron is L1 is equal to 1. And for the 3d electron, since this is again a single electron, we are using L2 because L is small, you see. So L2 will be equal to 2. And you know that for the p, the value of the orbital quantum number is 1, and for the d electron, the value of the orbital quantum number is 2. This is what you can see from this table. So when we are talking about p electron, it means that the value of small l is 1, and when we are talking about the d electron, the value of the orbital quantum number is 2. That's why we have these two quantum numbers over here, labeled as L1 is equal to 1 for the p electrons, L2 is equal to 2 for the d electrons. Now you see that these two electrons having orbital quantum numbers or the angular momentum quantum, or the orbital angular momentum quantum number as given by equation number 5.4, have the quantum number corresponding quantum numbers is L1 is equal to 1, L2 is equal to 1. So they will combine to give you the total orbital quantum number, which is capital L. So capital L will be equal to the mod of L1 plus minus L2. So the mod will be equal to 1 plus minus 2. If you add them, you will get 3. If you subtract them, you will get 1. And you need to write the values, the integer values between them. So I have obtained 3 values from this relationship, 3 to 1. If you add them, you get 3. If you subtract them, you will get 1. And you have also to write down the integer allowed values between these extreme values. So between 3 and 2, the value 2 will exist. So the capital L, which is the total angular momentum quantum number, orbital quantum number of the electrons having 2p and 3d electrons, is the 3 values are allowed, which is 3, 2, and 1. And the possible term symbols corresponding to these values of L will be F, capital F, capital D, and capital P. We are using a capital symbols for them because this is due to 2 electrons. And even if it exists for more than 2 electrons, we shall be using capital symbols as the term symbols. And you see that corresponding to 3, we have a capital, we have the term symbol F. Corresponding to capital L is equal to 2, we have the term symbol represented by capital D, and corresponding to the capital L is equal to 1, we have the term symbol corresponding to capital P. So these term symbols, that is F, capital D, capital P, will correspond to the quantum numbers capital L is equal to 3 to 1 respectively. And you know that from the table above, we have seen that when the value of a quantum number is 3, then of course the term symbol will be F. When the quantum number is 2, orbital quantum number is 2, the term symbol will be D. And when the quantum number is equal to 1, the term symbol will be P. Since in our case we are using more than 2 electrons, so since we are using 2 electrons, so we are using a capital F, capital D, and capital P. So capital letters will be used when 2 or more electrons are involved. And the angular momentum quantum numbers when 2 or more electrons are involved will be calculated using equation number 5.4. So this is the simple example that I have given, and we shall be frequently calculating such angular momentum, total angular momentum of the atom in the rest of the course on atomic physics. Now, lifting of orbital degeneracy by relativistic mass change. You see that in the previous slide we have said that these levels, for example, over here, that is n0, n1, n2, n3, and so on up to n, n-1, all these levels are degenerate. That is, they have the same value of energy. And you know that the second index in these parentheses, which is 0, 1, 2, 3, and so on up to n minus 1, represents the values of the orbital quantum number, as also shown in equation number 5.3. And you see that with the values of L, we have the same energy up to this point. But you know that this is not the case. The energy could be different, for example, as stated over here. That is the lifting of orbital degeneracy by the relativistic mass change. So here the relativistic mass change is responsible that different values of the orbital quantum number will have different energies. And this is due to the relativistic mass change. Up to this point, when we have said that all these have the same energies, that is n0, n1, n2, and so on up to n, n minus 1, have the same values of energies, because all these orbital quantum numbers are not affecting the value of the energies of the atom. But you see that now we are going to correct this statement, and because we are going to include the relativistic mass change, and due to relativistic mass change we shall find that the orbital quantum that the degeneracy is lifted, which means that the energy of these levels will now also will also depend upon the value of the orbital quantum numbers. So let's go through this one. Each level in the hydrogen atom or hydrogen-like atom is n-fold degenerate. This is what we have seen from the Grotrian diagram or from the term diagram given in slide number 1 and slide number 2 of this course. That is, the level were n-fold degenerate. That is, to each level there are associated various possibilities for spatial distribution of the electron, and the energy of the levels remain the same. So this is only the case when the relativistic mass were not included. That is, when we were assuming circular orbits according to the pure Bohr atomic model. So according to the pure Bohr atomic model, the levels are n-fold degenerate. That is, each level, for example, if you are talking about n is equal to 2, then there will be 2 levels according to corresponding to n is equal to 2. If you are talking about n is equal to 3, then will be 3 levels corresponding to n is equal to 3. And all the level corresponding to n is equal to 3, which are 3 levels, will have the same energies. So it means that there is n-fold degeneracy exists when we are talking about the circular orbits according to the Bohr atomic model. And but you know that now we are talking about the elliptical orbits, and in the elliptical orbits we shall see that we shall see that we have to involve the relativistic mass change, and under that condition the spatial distribution of the electrons will be different according to these n-fold degeneracy, and the energy of each level would remain the same only when the relativistic mass change is not included. But you know that the real problem is that we have to include the relativistic mass change. It means that the value of the total energy of the atom will now going to depend not only on the principal quantum number n, but will also depend upon the orbital quantum number L of the atom. And the degeneracy is lifted. That is why we call it, the topic is lifting of orbital degeneracy. Orbital degeneracy means that now the energy is also going to depend upon the orbital quantum number, and this will be due to the relativistic mass change. So the statement that I have given over here in this paragraph, that each energy is n-fold degenerate, that is correct. But you know that this is correct when we have not included the relativistic mass change, and the orbits of the electron are circular. But now we are going to include the elliptical orbits according to the Sommerfeld, and now the energy will depend upon the value of the orbital quantum number L of the atom due to either a single electron or due to multiple electrons. So this cannot explain a doublet or multiplet structure of the spectral lines shown in figure number 1 on page number 1. That is this. So you see that there are multiple structure in this diagram of the H alpha line obtained from the Bohr-Balmer series. According to the atomic theory of Bohr, there is only one single wavelength. But you see that due to high resolution spectrometer, we shall see that multiplets are existing. You can see if you only consider this peak and this peak, that is the two stronger peaks, you will say that this is a doublet structure. But if you try to include the other peaks, then you will see that it is a multiplet structure. So you see that this thing, that is the unfold degeneracy, this cannot explain doublet or multiplet structure of the spectral lines shown in figure number 1 on page number 1. Sommerfeld in 1916 noticed that m is not a fixed number, but m is a function of a velocity of the electron. So this is the concept of relativistic mass change. That is, there is a relativistic effect on the mass of the orbiting electron. So you see that this change of relativistic mass effect was introduced by Sommerfeld in 1916. Kepler's law. So you see that in order to explain these things, we are going through Kepler's law. Electrons are accelerated when they come nearer to the nucleus, and as a result of the Kepler's law of areas, the moving electron sweeps out equal areas between its orbit and the nucleus in equal times. So equal areas will be swept out by the electron in equal amount of time. So ultimately, when the electron is very close to the nucleus, the electron is accelerated because it has to sweep out equal area in equal amount of time. And since it is very close to the nucleus, so in order to sweep out an equal area, the electron has to be accelerated so that it can cover longer path of the orbit in the given amount of time. And this Kepler's law of areas is applicable to the gravitational objects. But here, Sommerfeld extended the laws the laws of Kepler area for the and applied it to the atomic case. That is the elliptical orbits. And when the elliptical orbits comes, that is when the electron in the elliptical orbit come closer to the nucleus, it has to be accelerated so that it can sweep out equal area in equal amount of time. And when it is further away from the nucleus, the electron will be moving slowly because now it is further away. It has to move slowly so that it can satisfy this condition, that is sweeping out equal area in equal amount of time. In the neighborhood of the nucleus, the electrons are thus faster and from special relativity more massive. So when the electrons are massive, that is when the electrons are moving with a much greater speed, then of course according to this condition that m is a function of m is equal to m of v, where v is the velocity of the electron. So now the value of m will depend upon the value of electron. So m is no more constant when the electron is approaching the nucleus. So under that condition, when m is a function of velocity of the light, you can regard such an electron as a massive electron. This is the term that was used at the time of the Sommerfeld. Now increased mass means smaller radius, because if the mass of the electron is smaller, it means that it is closer to the nucleus, having smaller radius and increased binding energy. So when the electron is closer to the nucleus, of course, it is strongly bound to the nucleus and having an increased binding energy. So the closer the electron to the nucleus, the smaller the radius it has and more increased binding energy. And of course, the mass of the electron will also be increased, that because the mass will now be depending upon the velocity of the electron, which is very high when the electron is approaching to the nucleus. The correction to the relativistic mass becomes more significant for smaller minor semi-axes. The relativistic mass change leads to a rotation of the perihelion point. Perihelion point is a point on the orbit which is closest to the nucleus. So you see that here we say that the relativistic mass change leads to a rotation of the perihelion point of the orbit and has a rosette motion about the nucleus, which is shown in the diagram below. Because the perihelion point is rotated and the orbit takes another shape. For example, you can see that the orbit is starting from here. It is going like that one, up, approaching at the largest distance from the nucleus. Then you see that the orbit is changing, the elliptical orbital is changing, and it approaches to the nucleus where it has gained maximum, where is accelerated and will gain a maximum velocity approaching closest to the nucleus. Then you see that it will go away from the nucleus, and because the perihelion point is rotated, and then of course the elliptical path is also rotated, or the elliptical orbit is also rotated, and this is like in the form of the rosette motion. And you see that here in this is the orbit, elliptical orbit of the electrons around the nucleus. The nucleus is represented by a red dot, and this cloud represented in blue, it actually represents the inner electronic shells of the atom, which you may assume that these are the closed electronic shells. So you see that here we have to apply the correction due to the relativistic mass. And the correction due to the relativistic mass becomes more important when the electron approaching to the nucleus is very high. That is when there is a high probability that the electron is approaching to the nucleus. And when this distance is very small, that is the distance of the orbiting electron from the nucleus is small, we must include the relativistic mass correction so that we can obtain correct energies of the electron. Including the dependence of electrons' energy on quantum numbers n and k. Now you see that here we have two quantum numbers. So now we are saying that the energy of the electron is not only earlier before said that the energy of the electron will depend only on the principal quantum number n. Now using the concepts of the elliptical orbits where the electron approaches very close to the nucleus, now we say that the energy of the electron will depend upon the two quantum numbers n and k. And to accommodate the effect of the relativistic mass as suggested by the Sommerfeld suggested the following changed formula of energy. Now you see that you have this formula suggested by the Sommerfeld. Now this formula says that the energy of the electronic orbit having elliptical orbit and approaching close to the nucleus will now depend upon the two quantum numbers n and k, where k is the quantum number originally introduced by the Sommerfeld. And you see that I have given you the relationship between k and n. K starts from 1, 2, 3 and so on, where the orbital quantum number which is related to the value of k. So L will start from 0, 1, 2, 3 and so on. So k can be replaced by L plus 1. Because we are no more using the quantum number k suggested by the Sommerfeld, we shall be using the quantum number L or the orbital quantum number L of the atom for the rest of the course on atomic and molecular physics. But now we are going to see the original formula suggested by the Sommerfeld in equation number 5.5, and let me read that one. So this is the energy E of the electron having depending upon the two quantum numbers n and k, and that is equal to mu times c square, where mu is the reduced mass of the electron, and then in the square bracket we have power minus the square bracket raised to power minus half, and within the square bracket we have 1 plus a term. In the numerator we have z alpha square, and in the denominator we have a square of n minus k plus the square root of k square minus the square of z alpha term. So this is the term, this is the energy expression that was calculated by the Sommerfeld. We are not going to we are not going in the detail of the derivation of this expression. We are just going to take it granted as grant take it, and let me explain the other terms. Here is capital Z is equal to atomic number of the atom. You see that this formula is again only applicable to the hydrogen atom and the hydrogen like atom. So here capital Z is the atomic number of the hydrogen like atom. Mu is the reduced mass of the system, that is the electron and the nucleus, due to these two systems forming a system. So this is mu is the reduced mass of the system. C is the speed of light. Nr, which we have not shown, but Nr is equal to n minus k, has a value of 0, 1, 2, 3, and so on, is the radial quantum number. K, which is equal to L plus 1. You see that here we are relating a K to the value of orbital quantum number. So K is equal to L plus 1 is equal to 1, 2, 3, and so on up to N. This is the azimuthal quantum number. So K, you may record K as the azimuthal quantum number, and N is equal to Nr plus K is the principal quantum number. So you see that we have related N to the value of Nr and K. If you put the value of the radial quantum number, you will get that the principal quantum number is there, independent of the other quantum numbers. But the other quantum numbers, for example, K and L, depend upon the value of a principal quantum number N. The principal quantum number, okay. Now you see that the alpha, which is given by E square over 4 pi epsilon naught into H bar square times C. If you substitute these values of H bar, C, and the charge of the electron, which I have presented in one of the previous slide, you will find that the value of the alpha is nearly equal to 1 over 100, 137. So 1 divided by 137. So this alpha is referred to as the fine structure constant, because with the inclusion of this alpha in the calculations, we can obtain results related with the fine structure of the spectrum. Now alpha is given by the ratio of two terms, that is the velocity of the electron in the first Bohr orbit divided by the velocity of light. So alpha, you see that is calculated from here, which is equal to 1, which is equal to the expression of which one is given over here, and it has a numerical value equal to 1 over 137. Equation number 5.5 can be represented in the following form. So you see that we can expand the terms in equation number 5.5 on the right hand side. That is, we can expand the terms binomially by using binomial series. We can expand the square bracket, and similarly we can expand the square root, which contains the term k square minus the square of z alpha square. This will also be expanded using a binomial series, or you can also expand simply because this is just only a square term, and then the square root that will appear in the expansion of this squared term will need to be expanded using a binomial series. So using a binomial series successively, you will find out this energy expression, that is E. Now depending upon the value of two quantum numbers n and k will give you a value which is equal to minus R times H times C, where R is the Rydberg constant of the hydrogen atom, H is the Planck's constant, C velocity of light multiplied by the Z square over N square. So you see that this is the original formula obtained by the Bohr atomic model. And minus sign indicates that this will give you the binding energy of the electron. And the first term, if you include the first term multiplied by this term, then of course this is the original formula of the energy of the binding energy of the electron due to the Bohr's atomic model. And now the other term, the second term, which is this term, contains alpha square z square over n square, and then in the parentheses we have n over k minus 3 over k. This is the term due to Sommerfeld atomic model, and then you can see that it involves two quantum numbers. One is the principal quantum number n, and the other is the quantum number k, which we have recorded as the azimuthal quantum number according to the statement of the Sommerfeld. But you know that here in this formula you can replace k with the value of L, that is k is equal to L plus 1. Then of course this becomes the formula that will be applicable in the today's notation. So you see that this second term include the terms due to the effect of the due to the relativistic mass change effect. And now the energy of the energy of the electron depends on two quantum numbers, n and k. And this is the simple, and this is the formula 70 given in 7.7. 5.7 has been obtained from the formula given over here, given in equation number 5.5, which is the simplified formula given in equation number 5.7. Now you see that you can see that the alpha square is present. So the value of alpha has already been given, which is equal to 1 over 137. And the square of this quantity will be very small. So you can see that the relativistic energy change, which is due to the presence of alpha square over here, is thus of the order of, that is, alpha square is approximately equal to 10 to the power of minus 5. So this is a small quantity but still observable. So you see that the second term is very small, but it is still observable, and you see that a final correction, a small correction due to the change of a relativistic mass can be included, has been included by the Sommerfeld. The higher terms can be computed, but of course at present these higher terms are not important. Now we shall talk about the limits of the Bohr-Sommerfeld theory. Because this is not a complete theory of the atomic model, there are some serious defects in the theories presented by the Bohr and the Sommerfeld. We are going to review those defects briefly, and also we are going to see the corresponding principle for the second time. For the first time, it has been discussed with much greater detail in one of the previous slides. Now we are going to just touch the concept of the Bohr of the correspondence principle, so that we can correlate our classical theories with the quantum theories. So this is the limits of the Bohr-Sommerfeld theory and also the corresponding principle. The Bohr-Sommerfeld model can predict only the emitted or the absorbed frequencies, but cannot predict. You see that this is now coming about the effect of these theories, but cannot predict their intensities or emitted or absorbed frequencies as a function of time. So these theories do not talk about these quantities, that is about the intensities or about the emitted frequencies or about the absorbed frequencies as a function of time. So we can say that I nu as a function of time, and nu A, which is the absorbed frequency as a function of time, and nu E, which is the emitted frequency as a function of time, are not available due to Bohr or the Sommerfeld model. So they are silent. That is, these two theories are silent about the emission of the intensities or the absorbed or the emitted frequencies as a function of time. The gap between the classical physics and the early quantum physics was bridged by Bohr's correspondence principle. So you see that it is the Bohr's correspondence principle that combines the two theories, that is the classical theory and the quantum theory. And under what conditions these two theories are combined, let's see. Early non-classical theory must every non-classical theory must, in the limit of high energies and small energy changes, yield the result of the classical theory. For example, at very high energies, and when the energies of such a system, that is when the changes in such energy systems is also very small, then we shall see that all the non-classical theories, for example, the quantum mechanical theory, will yield the same result as that of the classical theory. So the quantum theory and the classical theory will give you the same results under the condition of very high energies of the system. That is when the system is in a very high energy state. And the second is that when the energies of such levels are very small. That is we are talking about the continuum of energy. The intensities, polarizations, and the selection rules for spectral lines may be calculated from the laws of classical physics. Now you see that the classical physics is at a very advanced level. We can calculate these, that is, we can calculate the intensities, the polarization states, or the selection rules using, or for the spectral rules may be calculated from the laws of classical physics. And here the laws of classical physics doesn't mean that we are just talking about the Bohr and the Sommerfeld model. There are many other classical laws. So those laws can be used to calculate the intensities, polarizations, and the selection rules are related with spectral lines. Bohr-Sommerfeld could not explain correctly the spectra of even two electron atoms. So you see that this is one of the major defects, that the Bohr and Sommerfeld model cannot be used to explain the spectra of even two electron atoms. So if an atom containing two electrons, we cannot explain their spectra using the Bohr and Sommerfeld atomic models. Another point is that the magnetic properties of the atoms were not correctly described by the theories. Though we have not discussed the magnetic properties, maybe later on we shall talk about the magnetic properties of the atoms. But here we are just saying that the magnetic properties of the atoms were not correctly described by the Bohr's atomic and Sommerfeld models. These difficulties were removed by the modern quantum mechanics. So you see that the today's quantum mechanics talks about these difficulties and resolve them. Some of the Bohr-Sommerfeld results will remain valid, while others will be modified. So you see that very few of these, that is the Bohr's and Sommerfeld models, will remain valid. And we shall also talk about these validity of these things whenever it will be possible. But most of them will need a modification or a refinement in their descriptions. And this will be done through modern quantum mechanical approaches. So this is the end of slide number 6 of the course on atomic and molecular physics.